Hello everyone, welcome to a quick demonstration of expected result for Lab 5 Transistor Amplifier, which consists of mainly three parts. The common emitter amplifier, which is later followed by a buffer stage, and the common emitter biased using a current source. Some design goals are provided in the lab handout. For this specific implementation, I have targeted base voltage of 1/3 of the VCC, so the base voltage is supposed to be 1.6 volt, and considering a voltage drop of about 0.6 to 0.7 volt across the base emitter junction, the emitter voltage of the amplifier after proper biasing and correct implementation is supposed to be around 1 volt, 0.9 to 1 volt. These are the voltages that I check in conjunction with the collector voltage to justify my biasing condition and operating point of the amplifier. You should be careful for the base voltage. Actually, the ratio of R1 and R2 is important. Mainly, it is important to generate that specific voltage. However, you should avoid using extra large resistors for R1 and R2, as in that case actually the voltage will be affected by the base current of the transistor. So transistor resistors in range of, for example, 10K should be fine for this specific implementation, or even 1 or 2K. Here you can see an implementation of the amplifier. I also always use the channel 1 of oscilloscope directly connected to the source voltage, the signal generator output actually, and the channel 2 is going to be connected to different output node of the circuit for each step. I start justifying the implementation by checking the DC voltage at base. As we mentioned, for our design target, it should be around 1.6 volt, and here we have a voltage of, as you see on the digital multimeter, it's showing a voltage of 1.5859, which is as expected. Then the emitter voltage, also as expected, is around 0.9 volt. It is indicating the transistor is properly biased according to our design targets. Also, you can check the collector voltage. 1.6 is also what is consistent with the selected value for the collector resistance in my design and the target biasing current. For the signal generator, do not forget to use the main output connected to your circuit. Also, to generate low amplitude signals, you need to activate the -20 dB attenuation provided on the signal generator panel. On the oscilloscope, always start by pressing the storage button followed by the default setting to load the default setting of the oscilloscope to prevent any unintended setting that may be applied by previous user of the oscilloscope. Then you should set the horizontal resolution to some values comparable to the period of your signal. Here we have a 1 kHz sine wave with a period of 1 millisecond, so I have set the horizontal resolution to 500 microsecond. You should make sure the attenuation settings on the oscilloscope screen are matched with the setting on your oscilloscope probe. Also, you can turn the bandwidth limit to reduce the noise and have a much more stable signal on the oscilloscope screen. For channel 2, because it is going to measure the output signal, which is associated with some DC level, you can change the coupling to the AC mode to remove that DC component and zoom into your signal easier. Then it's recommended to set both channel scaling at the same range, so you can easily compare the magnitude, peak amplitudes, and also instantly have some insight into the gain of the amplifier. If you want much better noiseless signal, you can turn the averaging mode on after you have some fixed waveforms on your oscilloscope screen. For doing your measurements, I suggest you using the left hand side menu on the oscilloscope screen, so you can switch between vertical menu, which contains peak to peak measurements. If you are going to measure some frequencies, you can use the horizontal menu. For each channel, you can first select the channel, then add appropriate measure to your oscilloscope screen. Oscilloscope screen is showing the input waveform in yellow and the output waveform in blue. The peak-to-peak input is about 200 and the output peak-to-peak is 700 millivolts, indicating a gain of about 3.5. The next step, you are supposed to add a buffer stage to your common emitter amplifier. The buffer is actually a common collector amplifier or emitter follower. Each is capable of deriving low impedance resistance like the speaker that is going to be connected to the output of this circuit. You can see the output voltage when the speaker is connected to the amplifier, so the gain is significantly reduced, and also you observe some distortion for negative cycle of the sine wave. The gain reduction is mainly because of the low impedance associated with the speaker. So as I disconnect the speaker from circuit, the amplitude increases. In this case, with speaker disconnected, we only have a 1K resistor as a load of the source follower amplifier. But as soon as I connect the speaker in parallel to the 1 kilo ohm resistor, the amplitude reduces significantly. Also, you can see how the speaker responds to different frequency of the source signal. And here is a quick test of connecting the output of handheld radio to your amplifier. For the last part of this lab, we are going to replace the emitter resistor of the common emitter amplifier with a current mirror. Then we are going to deal with this amplifier in two different modes. One in common collector mode, and where the amplifier works as a buffer, and we should expect a gain of around 1 out of it. And the other mode is the common source amplifier, which is the common emitter amplifier, which is biased using a current mirror. In that case, you need to put a bypass capacitor in parallel to the current mirror at the emitter of Q1, and we should expect a high gain out of this amplifier. For the first case, in common collector mode, you need to put the channel to the output in the DC coupling mode, so you can see the difference, the DC offset between the input signal and output signal, and the relative gain should be close to 1. After adding the bypass capacitor to the emitter of the amplifier and measuring the output at collector, you may notice a significant distortion as a result of the high gain of this amplifier. So you need to reduce the input amplitude to avoid this condition. And afterward, when you have justified output signal without any distortion, you can measure the amplifier gain. To do so, you may need to increase this signal generator attenuation by pushing the -40 dB button, so you can generate much smaller input signals. And after applying proper setting to your setup, you can measure the gain of the amplifier. As you can see here, the input amplitude is around 20 millivolt peak to peak, while the output is around 900 millivolt peak to peak. A gain of about 45 can be achieved out of this circuit.